Hey everyone, and welcome to The Explainer. I am absolutely thrilled you're here today. We are taking a journey into the invisible, microscopic physics that literally shape the built environment all around us. If you've ever looked at a massive steel bridge, a spacecraft, or, even just the pan you use to cook your morning eggs, and wondered how engineers know exactly what materials will survive extreme heat, well, you are in the right place. We're going to decode the secret thermal lives of metals, ceramics, and polymers. Okay, let's dive right into this. Look at these solid steel railway tracks. They are completely warped and buckled out of shape. And the crazy thing is, no giant machine came along and bent them. This dramatic engineering failure was caused by nothing more than a sunny day. We so often think of heat just as a cozy feeling of warmth, right? But as we can clearly see here, heat is a massive, relentless physical force that has the power to move and deform solid metal. Which actually leads us to a pretty fascinating question. Why does invisible heat have the power to bend solid steel? To answer this, we're going to use what I like to call a macro, micro, macro loop. We'll start with big, real-world problems, zoom all the way down to the atomic level to see how atoms behave, and then zoom right back out to see how that atomic behavior dictates human engineering. So, here's our quick roadmap for today's explainer. We'll start with 1. The invisible power of heat. 2. Heat capacity, absorbing energy. 3. Thermal expansion, growing with heat. 4. Thermal conductivity, moving heat. And finally, 5. Engineering our thermal world. All right, let's kick things off with section 1, the invisible power of heat, looking at heat as a physical force. Before we can really understand how materials react to heat, we kind of have to define what we're actually looking at when we say something is getting hot. The core concept you need to know is that heat is a form of energy. Specifically, it's energy that comes from the motion between particles of matter. Temperature? Well, temperature is just a measurement. It simply measures the intensity of that heat, which correlates to the degree of motion between those particles. So whenever we talk about a material heating up, we are really talking about its atomic particles moving and vibrating more vigorously. That right there is the foundation for everything we're about to cover. Moving right along to section 2, heat capacity, absorbing energy. You can actually think of different materials as being like completely different sized sponges for thermal energy. By definition, heat capacity, which we represent with the letter C, is the amount of energy required to produce a unit temperature rise. It's essentially a material's energy sponge capability. So the crucial point here is that this property dictates a material's ability to absorb heat from its external surroundings. And when we measure this per unit mass, we call it specific heat capacity. Just look at the stark contrast in these numbers for specific heat capacity at room temperature. Aluminum, a standard metal, takes 900 joules per kilogram Kelvin. Alumina, a ceramic, takes 775. But look at polypropylene, a polymer. It requires a massive 1925 joules. The polymer needs significantly more energy to raise its temperature compared to the metal or the ceramic. It's a much bigger sponge. Let's put that into a bit of real-world math to give you a sense of scale. If you want to heat 5 kilograms of material by 130 degrees Celsius, aluminum only requires 585 kilojoules of energy. But to heat the exact same mass of polypropylene by the exact same amount, you have to pump in 1,251 kilojoules, literally more than double the energy. Why is that? Well, the secret lies in the atomic bonds. Covalent bonds in polymers just don't let atoms easily exchange electrons the way metallic bonds do. So they just sit there and soak up massive amounts of energy before their temperature actually rises. Now, let's zoom back out to the macro scale. This mathematical reality impacts literally everything around us. It's the whole reason our oceans, which have a super high heat capacity, can absorb massive amounts of solar heat without boiling, which is what stabilizes Earth's climate. It's why a pot of water seems to take forever to boil, but the metal pot holding it, thanks to its low heat capacity, gets scorching hot almost instantly. And for engineers, understanding this energy sponge effect is absolutely critical for designing materials for things like spacecraft cooling systems, where managing intense heat is quite literally a matter of survival. Okay, on to section 3, thermal expansion, growing with heat. Remember those bent railway tracks from the very beginning? Well, we're going to address that right now by zooming all the way down to the atomic level to see how materials physically grow with heat. As materials get hotter, their atoms vibrate at really high frequencies. A single quantum of this vibrational energy is called a phonon. You can think of a phonon as being kind of analogous to a photon of light, but for vibration.
It represents the coordinated atomic jiggling inside solid materials. And as things heat up, these elastic lattice waves propagate through the crystal at the speed of sound.
Now, what's really interesting about this is seeing those phonons in action. You can see the normal resting lattice positions of the atoms in orange, and then their displaced positions due to vibrations in blue. The atoms aren't just sitting still, they are constantly vibrating. And as they absorb more heat, the amplitude of those vibrations increases, generating these distinct waves throughout the entire structure of the material. So why exactly does that atomic vibration cause the entire object to expand? Looking at this potential energy trough perfectly explains it. Notice how the red curve here is uneven. It's not perfectly symmetrical, right? As the temperature goes up and atoms gain more of that vibrational energy, moving from E1 up to E2, E3, and so on, the average interatomic distance, which is represented by R, shifts over to the right. Because the energy curve is steeper on the left and shallower on the right side, the vibrating atoms literally push each other further apart as they heat up. And just like with heat capacity, different materials behave very differently here. If atoms are strongly bonded, like we see in ceramics, that trough is deep and narrow, which means they don't move apart very much. They have a low coefficient of thermal expansion. But polymers? Polymers expand drastically more than metals or ceramics. This is because their secondary intermolecular bonds are incredibly weak, and they have minimal cross-linking. That allows the atoms to easily push each other wide apart when they get heated.
And this brilliantly illustrates how engineers use this atomic physics to our advantage. What you're looking at is a bimetallic strip used in everyday thermostats. Engineers take two metals with totally different expansion rates, like steel and copper, and they bond them firmly together. When they heat up, the copper expands a lot more than the steel, which physically forces the flat strip to bend. That simple bending motion is what mechanically turns the dial on a thermometer or clicks your heating system off. We quite literally turned atomic vibration into functional mechanics.
All right, section 4, thermal conductivity, moving heat. So far, we've explored how materials hold heat and how they grow with heat. But now, let's look at how they let heat travel right through them. Thermal conductivity, denoted by the letter K, is the rate at which heat is conducted through a material. According to Fourier's law of heat conduction, heat always flows in the direction of decreasing temperature, so from hot to cold. In solid materials, this heat transport relies on two main things: those vibrational lattice waves we just talked about, the phonons, and the movement of free electrons. I mean, just look at this mind-blowing contrast. The thermal conductivity of silver, a pure metal, is 410 watts per meter Kelvin. Meanwhile, the thermal conductivity of polypropylene, a polymer, is just 0.12. Silver's ability to move heat is massively, fundamentally, vastly superior to the polymer. It's not even close. To understand why there's such a huge gap, we have to look back at the atomic structure again. Metals contain massive amounts of free electrons. These electrons act like rapid heat highways, zooming thermal energy across the material almost instantly. That's why the purest forms of metal are the absolute ultimate conductors. On the other hand, ceramics and polymers, they completely lack these free electrons. They have to rely solely on phonons to transfer heat. Furthermore, amorphous ceramics have highly disordered atomic structures that actually scatter those phonons, and porous materials trap air, making them incredible thermal insulators rather than conductors.
Connecting this atomic theory back to human-scale technology is where this stuff gets really fun. We intentionally exploit these properties every single day. We choose high-conductivity aluminum and copper for computer heat sinks to rapidly pull destructive heat away from our processors. We choose low-conductivity materials like wool for our winter clothing to trap our body heat, and foam or fiberglass to insulate our homes. And in aerospace and automotive engineering, teams use a highly complex mix of both conductors and insulators to manage extreme engine heat and keep vehicles from literally melting out of the sky.
Which brings us to section 5, engineering our thermal world.
Let's bring all three of these core concepts together. This explainer has taken us from warped steel train tracks down to vibrating atomic phonons and back up to spacecraft design. The major takeaway I want you to have here is that the mathematical formulas dictating phonons, free electrons, and molecular bonds, they are the literal building blocks of our safe infrastructure. Mastering heat capacity, thermal expansion, and thermal conductivity isn't just academic physics. It is the very foundation that allows us to build a modern, robust, and technologically advanced civilization.
As we wrap things up today, I want to leave you with this one thought. We are constantly pushing our machines faster, deeper into space, and into way more extreme environments than ever before. So based on the thermal properties we've uncovered today, what radical new materials do you think we'll need to invent to survive the heat of tomorrow? Thank you so much for joining me on this explainer. Keep asking questions and keep learning.